not used in modern operating systems, but definitely modified versions of exist. Do we get swapping on mobile systems? Can you get it in Android, iOS, things like that? No. The reason is that you don't want, and I'm probably one of the biggest constraints here is our flash memory. Flash memory has this limited number of writes. So every time you write stuff to flash memory, it decreases the lifespan of the flash memory. Same with SSDs, by the way. But flash memory is a bit worse. So we want to minimize the amount of times that writing back into secondary storage actually occurs on mobile devices. That's one of the reasons. Another reason is that your flash memory isn't typically that large. So just setting aside some place on your flash memory just for swapping isn't always realistic. And it's typically also not that fast with throughput between the flash memory and the CPU on mobile platforms. And typically what operators do is they ask the process to voluntarily relinquish certain allocated memory to them. Not that important, but what's important that I want you to understand is that with mobile operating systems, you typically don't get much swapping happening. There's other means that they use to implement it. Right, so this brings us to an implementation of how memory was managed, from one of the earlier type of operating systems. In this case, the principle was that your memory, and this we see now, must contain at least the operating system, but also your application. Somewhere in this memory, the application must exist. And contiguous allocation was one solution used by early operating systems to help us with this. And normally, the main memory was broken into two partitions. The operating system was in one of these partitions, typically held in low memory. So this was exactly how MS-DOS functions work. So MS-DOS first was loaded from memory location 0 up to, I think, 640 kilobytes, or even lower than that, sorry, a lot lower than that. And then your application used to be loaded on top of that. So the user application is then held in what they call high memory, the memory addresses that's in the higher areas. Each process was contained in a single contiguous section of memory. That's what I want you guys to realize. So we've got a process, think of it as a big monolithic block. That block needed some space in memory. And that block had to be contiguous. That's the idea. So note that. It's not broken up into smaller pieces. One contiguous area. The relocation registers were used to help protect the user processes from each other. So if you have, let's say, 4 processes, each process had its own value of the relocation register, and the relocation register helped ensure that the areas in which they are loaded in memory were different, but you also had limit registers. So in this case, the text, the lecture notes mentions a base register. The good base register was used earlier in this chapter, but the base register and relocation register is exactly the same. But just note that it's the base register for that process. Limit registers helps to ensure that the process, when they make a request, that request's address isn't higher than. That's weird. We have things happening here in the that doesn't overwrite the address allocated to it. For instance, this is the basic algorithm that was used. So remember logical address and physical address? What component does this? What component does that? Not the ALU. The MMU, the memory management unit. So the memory management unit did this calculation for every address that was active. So you got a logical address. The first thing that the MMU did was it checked, is this address smaller than the limit register? If I want to access something in memory address 4000, it first looks at the limit register. If that limit register has, let's say, a value of 2000, then I know I'm going to jump above the memory allocated for this process. So the limit register really just tells me how big a memory address can be before I start potentially going into someone else's memory address. If it is smaller than that, then I add the logical address to the relocation register and then give you my physical address. That's really how this relocation works. If obviously the value was greater, then what they call a trap occurs or an interrupt occurs, because then you've got a general protection of the where memory doesn't fit in there. So this is logically how potentially it looks like. We always have the operating system in here. We have a number of processes, each in a contiguous area. You can see here, process 5, everything, all the code, all the data belonging to process 5 was in this section of the memory. Process 8 was in that section, and process 2 was in that section. They call variable partitioning. The principal idea of that is that each process is assigned a variable size, meaning whatever you need, that is the partition size that you need, that it will get. The principle of a whole, what is a whole? A whole is a block of available memory. So for instance, let's say process 8 was running here, and we swap process 8 out, or it's finished running, or whatever, then we get this whole that is available in our computer memory, our physical memory. Now, when we get such a whole, then this whole becomes available for another process to be loaded into, which is process 9, and then later on will be process 10, and so forth. And that is how we can allocate memory for our, or this how allocation works. The operating system basically keeps track of the allocated partitions, so it keeps track of where memory is being used, and also where memory is available. That's called repartitions. So let's. The question is, how does the operating system know where and how to fit process into the whole? Because there can be different holes. You get what they call the first fit allocation algorithm. The other one is called the best allocation, and the other one is called the worst fit allocation. So just quickly, what does first fit mean? So as you get processes that needs to be swapped into, it looks at the holes in a list, so you can keep track of the holes in a linked list, for instance. It starts at the beginning of the linked list, and it finds the first node in the linked list that is greater than the actual memory that you need. That's called first fit. Best fit means it runs through the whole linked list, gets all the memory addresses that's bigger than the one that's been requested, and use the one that is the closest to what we are actually requesting. I'll demonstrate this in just a moment. And then worst fit, again, runs through the whole process, tries to find again all the memory holes that's greater than the process that we require, and use the worst one. Why do we want sometimes the worst one? The largest one. Because what is then left is also potentially a large hole again. We've got a small hole that we need. Alright, so let's quickly just demonstrate potentially how this can happen. So for this, let's use Excel as a teaching tool. So as soon as I switch away from this, don't know, you may get questions that's got something to do with this thing. Right, so what we see here is a linked list. It doesn't look like a linked list, but it is. This linked list contains 7 different nodes. Let's call them A, B, C, D. Each of these linked lists, each node has a value. So this node has 6, meaning there's a whole of 6. Actually, it's a little bit more complicated because each of these nodes says where the starting memory is and the end memory, and then the side as well. Because sometimes it will actually merge some of these off. So that's beyond the scope of what we're doing. Now, first let's just worry about algorithms. So here we've got a bunch of nodes with different hole sizes. And here we have the requests. So the top is the first request, middle is the second request, the bottom is the last request, 15, 17, and 18. let's figure out which hole